All right, now we're going to go through the examples. And remember, with this question, we have the coefficient of kinetic friction, the coefficient of static friction, and we are looking for the magnitude of acceleration. We also know the mass of the crate, the pulling force, and the angle. So we already have our free body diagram. And what I want to do is, first, I want to calculate the maximum amount of static friction, which is equal to the coefficient of static friction times the normal force. So we know the coefficient is our 0.5, but we need the normal force to be able to plug in here. So the normal force comes from the vertical net force equation. So we're going to say up is positive, down is negative. So we're going to have the normal force minus or plus the vertical component of the tension. So that's going to be Ft sine theta minus the weight force. And so now for our friction calculation, we need to solve for the normal force. So that means we are going to subtract Ft sine theta from the other side and add mg to the other side. So we're going to get the normal force is equal to mg minus Ft sine theta. So this is our equation for the magnitude of the maximum static friction. So we can plug in our numbers, and this is going to be 0.5 times 40 times 10 minus our 100 newtons times the sine of 30. And doing that calculation, you should get 175 newtons. So we need to see if the pulling force is going to be greater than 175 newtons. If it's not, this isn't going to move. So the pulling force is going to be the horizontal component of tension, which is Ft cosine theta. So Ft cosine theta is going to be 100 newtons times the cosine of 30. And when I calculate that, it's going to give us 86.6 newtons. So the pulling force is significantly less than the maximum amount of static friction. So if I pull with 86.6 newtons of force, this is not going to move. It's not going to move. So that means the acceleration is going to be 0. Now, if this was already moving, so say for example, it's already moving with a velocity of 1 meter per second, then all of our calculations would be for kinetic friction. So let me erase everything here. And let's do this as if it's already moving with a velocity of 1 meter per second. The velocity doesn't matter. We're just saying it is moving. So let's calculate the acceleration using kinetic friction now because it's moving. So our normal force, the equation is going to be the same. And now for our horizontal force, we have the pulling force, which is our Ft cosine theta, minus friction, and now it's going to equal mass times acceleration. So now we can go ahead and try and solve for the acceleration. Problem is, we need to substitute something in for friction. So we have our Ft cosine theta minus, and instead of friction, let's go ahead and use our fun equation. So I'm going to plug in the coefficient times the normal force. That equals ma. I'm going to go ahead and divide by m. So Ft cosine theta minus the coefficient times the normal force, and all of this is going to be divided by m. Now, we have to plug in the normal force. So the acceleration is going to be Ft cosine theta minus the coefficient times the normal force, which we already found earlier, and that's going to be mg minus Ft sine theta. All of this divided by m. So when you get these problems with friction, this is where I keep saying they're not quite so fun, because the equations end up looking icky because there's so much in them. So you can go ahead and plug in numbers now, and we already know that the Ft cosine theta was 86.7 or 86.6 newtons. And if I do this one, I believe it's 52.5. I believe it's 52.5. And we know our mass is 40. So this would be 86.6 minus 52.5, and divide that by 40. And so the acceleration would be 0.85 meters per second squared. So if it's moving, the 100 newtons at a 30-degree angle is enough to keep it moving, or to keep it accelerating. All right, this one's a little bit different. So with this question, you're going to be deriving an equation for the coefficient of kinetic friction. So specifically, we have a block of mass m that's pushed across a rough horizontal surface at a constant speed by a force that is magnitude F at an angle 30 to the horizontal. The coefficient of kinetic friction between the block and the surface is. So we are going to be deriving an equation for that coefficient of kinetic friction. So you can do this using this whole method we did here. It's just once you get your equation, you have to do the algebra to solve for mu. And this one, it's not going to be accelerating, but yeah, you can basically use this method of substitutions. Or I'm going to show you a slightly easier method that helps with the algebra. So the other thing is when you are given variables like this, so they're identifying knowns. Even though they're just giving you a variable, not a number, we still call these knowns. So our final equation can only contain the variables that are given and any other constants like g. G is a constant, so it's always allowed, or a half or 2. Those are things that are going to be allowed. So since we're looking for the coefficient, we are going to need to use the fun equation because that's where we find that coefficient. So to make this a little bit easier, what we're going to do is we are going to do this part of the algebra to start with. I'm going to solve for the coefficient of friction. And so the coefficient of friction is equal to the force of friction divided by the normal force. So when we now have this problem, if you think about the force of friction, back here when we did our net force equations, friction, the force itself, is in our horizontal net force equation. Down in the denominator, we have the normal force. Well, the normal force comes from the vertical net force equation. So what we're going to be doing now is we're still going to do our horizontal and vertical net force equations, but we're going to do them and then plug them into this equation. So here's my vertical net force equation. So here's my free body diagram. Here's my force is downward this time. Here's my weight force. Normal force is upward, and friction is this way. So positive, positive. So the horizontal net force equation, we are going to have the pulling force, or the component of the pulling force, F cosine theta, and then we are subtracting friction, and in this case it is a constant speed, so they equal 0. So if I solve for friction, friction is going to equal F cosine theta. And so that is what I'm going to put on top, F cosine theta, done. Now for the vertical net force equation, we are going to have the normal force in the positive direction. The component of the pulling force is going to be in the negative direction this time, and the weight force is in the negative direction, and they're equal to 0. Solving for the normal force, I add both of the others to the other side, so the normal force is equal to mg plus F sine theta, and this is what I substitute here, mg plus F sine theta, and that's it. This is my equation for mu. It just saves you some of the messiness of the constant substitutions.